So, I want you to picture something. If you point a camera at a static TV screen, just that meaningless, snowy, black and white noise, a computer will actually use significantly more memory to save that chaotic image than it would use to save, like, the entire text of a Shakespearean play,
Oh, easily.
which is crazy. Let
Yeah.
that sink in for a second. And the reason is, to a computer, perfectly remembering pure chaos is literally the hardest task in the universe.
Right, because there's no pattern.
Exactly. There's no pattern to latch onto. There's no shortcut.
Yeah.
But humans, we don't work like that at all. If you ask a human to describe the TV static, they don't list the exact position of every single black and white pixel.
No, they just say, oh, it's static and walk away.
Right. They just move on with their lives. So for this deep dive, we're going to explore how to bridge that massive gap. We're going to figure out how to teach a machine to, well, to stop memorizing the noise and to actually start understanding the world.
And honestly, that is the defining challenge of artificial intelligence right now. I mean, we've spent decades building these machines that are incredibly good at recording vast amounts of information, but recording is fundamentally different from comprehending.
Totally.
To cross that threshold, an AI actually has to learn how to forget. It has to learn how to abstract.
Yeah, and that brings us to our specific mission today. Welcome to the show, everyone. Now, we have a very targeted, highly specific audience for this one. We are speaking directly to the Bussin' Sigma scholars of Edward Little High.
A very ambitious group.
Oh, absolutely. We know you guys are at it again. You aren't just writing like a script to automate your homework or scrape some websites.
Yeah.
You've embarked on this wildly complex Python coding project. You are trying to connect the absolute bleeding edge of abstract mathematics, information theory, and AI into one unified framework.
Which is a phenomenal undertaking for any developer, let alone scholars at your level. I mean, you're attempting to programmatically illustrate the deep structural relationships between some incredibly dense mathematical concepts.
Yeah, we're talking sigma algebras, the Borel sigma algebra, lossy
Yeah.
compression, the heavy hitters.
Exactly. And you're doing all of this to mathematically and programmatically prove two monumental statements.
Right. The first statement being, quote, compression is intelligence.
And the second statement, which is really the ultimate corollary to the first, is, quote, lossy compression is intelligence where sufficient information is retained to perform the expected outcomes.
Right. So compression is intelligence. On the surface, that just sounds bizarre.
It does.
Because when most people hear the word compression, they think about, trying to shrink a massive 4K video file so they can attach to an email without the server yelling at them.
Right. They think of zip folders.
Exactly, zip folders on a desktop. But in the realm of universal artificial intelligence, compression isn't just a storage trick. It is the literal mathematical definition of learning.
It is. And to understand why that's true, we have to completely rebuild our conception of how a machine interacts with reality. Like, you can't just feed an AI a massive CSV file of data and hope it magically becomes intelligent.
Yeah, it doesn't work like that.
No. The machine first has to understand what information actually is at a foundational structural level. It needs a mathematical framework to define what is knowable and what is unknowable. And that, fundamentally, is the role of sigma algebras.
Right. And then, once it knows what information is, it has to figure out how to handle the infinite continuous physical world. Because the real world isn't neatly categorized into discrete rows and columns.
Not at all.
It's messy. And if an AI isn't careful, the infinite nature of physical reality will literally cause its logic to break down. And that is where the Borel sigma algebra comes into play.
Exactly. And once it constructs that safe, rigorously defined mathematical universe, then it has to learn how to recognize patterns within it. That's the domain of lossless compression. That's where the AI tries to find the absolute shortest possible explanation for the data it sees.
But, and this goes back to our TV static example, lossless compression has a fatal flaw.
It forces the AI to memorize the noise.
Right. So to achieve true human-like abstraction, the AI must learn the art of intentional ignorance. It has to learn how to throw away the static while keeping the underlying message, which is lossy compression.
It's essentially a literal architectural blueprint for a digital brain.
It really is. And since the Sigma scholars of Edward Little High are actually coding this in Python, We aren't just going to talk about this in abstract philosophical terms. We're going to walk through the exact conceptual architecture you need for this project.
We're going to translate high-level mathematics into classes, methods, variables, and algorithms.
So open up your IDEs, fire up your virtual environments, and let's start at the absolute bedrock. Let's define the foundation of knowledge itself.
So if we're going to build an intelligent agent in Python, we can't just start with neural networks or backpropagation.
Yep.
We actually have to start with measure theory. We have to define the universe of things the AI can possibly know. In math, this begins by defining a probability space, which rests on something called a sample space, usually denoted by the Greek letter omega.
Omega, right?
Yeah, and the sample space is simply the set of all possible outcomes of a given situation or environment.
Okay, let's ground that. So if our AI is trying to understand a super simple game like rolling a standard six-sided die, omega is just the set containing the numbers 1, 2, 3, 4, 5, and 6.
Exactly.
That is the entire universe of possible outcomes.
Right, but just having a list of raw outcomes isn't enough for an AI to actually reason about the world. Like, let's say that AI wants to know if the roll was an even number.
Okay.
Well, even number isn't a single outcome. It's a collection of outcomes, specifically 2, 4, and 6. So the AI needs to be able to ask questions and define events. This collection of subsets, these events that the AI can perceive and measure, is what we call a sigma algebra, which is typically written as a script F.
Wait, hold on. Let me jump in here. Because as a programmer, I'm thinking, why can't the Python program just look at the incoming data as a giant unstructured list of things that happened?
Right.
Like if the die rolls a 4, the program logs a 4. Why do we need to build this whole secondary structure of subsets and call it a sigma algebra? What's the actual computational point of doing that?
It really comes down to logical deduction. A sigma algebra is the rigorous mathematical representation of an information state.
Okay.
An event is only considered measurable, meaning the AI can assign a probability to it, update its weights, and actually learn from it, if the AI possesses enough structural information to definitively say whether that event occurred or not.
I see.
If you just have a raw list of data without the relational framework of a sigma algebra, your AI can't perform basic logical inferences. It can't say, because A happened, B definitively did not happen. The sigma algebra sets the strict boundaries of what is logically computable by the agent.
Okay, that makes a lot of sense. So for the scholars listening, I want you to think of it like this. Imagine you are a student in a biology class at Edward Little High.
Great analogy.
The sigma algebra is basically the syllabus for that specific class. If there's a highly complex astrophysics formula, and it's not on the syllabus, meaning it's not in the sigma algebra,
Yeah.
you literally cannot be tested on it.
Right, it's completely unmeasurable to your grade.
Exactly. Even if that astrophysics knowledge exists out there in the broader universe, relative to your specific classroom environment, it doesn't exist. You don't have the framework to process it. So your Python program is that student, and the sigma algebra defines exactly what it's capable of being tested on.
That is a perfect way to conceptualize it. But here's the catch. You can't just throw any random collection of subsets together, call it a syllabus, and expect to have a mathematically sound AI.
Right.
A valid sigma algebra has to obey 3 strict, non-negotiable mathematical axioms. If any of these 3 are violated, the AI's internal logic will eventually contradict itself, and the whole probability model collapses.
And this is exactly what you are going to code in your very first Python class. Let's imagine you create class sigma algebra. When you initialize this class, you pass it your sample space, your omega.
Yes, maybe passed is a standard Python set.
Yeah. But then you have to write internal validation methods to mathematically prove that the collection of events you generate from that space is actually a valid sigma algebra. So let's break down those 3 golden axioms. What is axiom number 1?
Axiom number 1. The collection of events must contain the empty set.
Okay.
Mathematically, this is denoted by that symbol representing a circle with a slash through it. Philosophically and programmatically, this means that the event of nothing happening, or no outcome occurring from our defined set, must be an explicitly measurable, knowable state.
So in Python terms, your collection of events, which you could store as a list of Python frozen set objects to make them hashable and immutable, must literally contain an empty frozen set. Because if your Python program can't comprehend the mathematical absence of an event, it can't fully comprehend the space of possibilities. It has to know what nothing looks like. That seems straightforward enough to code.
Yeah.
You just append an empty set to the list. What's axiom 2?
Axiom 2 is that the collection must be closed under complements.
Closed under complements, meaning
It means if an event A is in your sigma algebra, its absolute opposite, the non-happening of A, must also logically exist in the sigma algebra.
Oh, I see.
Like, if your AI agent is assigned to measure the probability that a stock price will go up tomorrow, it mathematically must possess the structural capacity to measure the probability that the stock price will not go up tomorrow. You can't have one without the other.
Right.
In set theory terms, if A is in your collection, then omega minus A is also in your collection.
Okay, let's talk about the Python implementation for that, because this is where the computational rubber really meets the road for the scholars. If they're writing a validate complements method inside their class, they need to iterate through every single subset in their generated collection.
Yes.
And for every subset A, they take their base universe, their omega, and subtract A, using Python's native set difference operation.
Correct.
Then they check if that resulting set is also present in the collection. If it's missing, the program should immediately raise a value error or something,
Right.
because it's an invalid information state.
Precisely. That validates the second axiom. Now, the third axiom is the most complex, and it's actually where the sigma in sigma algebra comes from.
All right, lay it on us.
The collection must be closed under countable union.
Countable unions. Break that down for us.
It means that if event A can happen, and event B can happen, and event C can happen, and they are all measurable within your sigma algebra, then the combined compound event of A or B or C must also be in the sigma algebra.
Okay, so chaining them together with OR logic?
Right. And this rule holds true even if you have a countably infinite sequence of these discrete events. If you can measure individual isolated events, the logic of probability strictly dictates that you must be able to measure any logical or R combination of them.
And because of De Morgan's laws in set theory, which basically connect unions and complements, this third axiom automatically implies that your sigma algebra is also closed under countable intersections, right?
Exactly.
So if your AI can measure the compound event A or B, it structurally possesses the ability to measure the intersecting event A and B.
Yes. The closure under unions combined with the closure under complements guarantees the closure under intersections. It weaves this totally airtight logical web.
But I'm looking at this from a coding perspective, and I see a massive computational trap here. If you're writing a valid unions method and your omega space has, let's just say, 100 distinct elements, the total number of possible subsets, the power set is 2 to the power of 100. That is a number so astronomically large that it exceeds the memory capacity of every computer on Earth combined. You physically cannot iterate through 2 to the 100th power combinations to check for union closures. The Python script would just hang forever.
You've hit on a very crucial distinction between pure mathematics and applied computer science.
Right.
Because in pure math, we simply declare that the sigma algebra is generated by the subsets and the axioms hold. But in Python, as you pointed out, you cannot explicitly generate and validate the full power set of a large sample space.
So what's the workaround?
Instead of exhaustively listing every possible event, your sigma algebra class needs to be designed generatively. You don't store the entire collection in memory. Instead, you write a function, like isMeasurableEvent, that checks if a newly observed event can be constructed from a set of base generators using unions and complements.
Oh, that's clever.
You validate the rules of construction, not the entire realized space.
That is a critical tip for the scholars. Don't try to store the whole universe in a list. Store the laws of physics that govern the universe and test against those laws on the fly. Now, once you have this mathematically airtight, validated sigma algebra, you can finally introduce what's called a probability measure. Right.
Right. A probability measure is just a function that maps any valid event within your sigma algebra to a real number between 0 and 1.
Where 0 means impossible and 1 means certain.
Exactly. And because the sigma algebra obeys those three axioms we just talked about, the probability measure will behave consistently. The probability of an event and its complement will always sum to exactly 1.
Okay, awesome. So we've built the foundation. Our Python AI now has a rigorous syllabus. It knows how to define an event, it knows what nothing is, and it knows how to logically combine events without contradicting itself.
A great start.
But here's the major problem. This works beautifully for finite spaces. It works for rolling dice, drawing playing cards, or reading discrete categories from a simple database.
Yes, finite spaces are pretty trivial in measure theory.
But the real world, the actual physical environment that a true artificial general intelligence needs to navigate, is not a finite list of discrete events.
No, it's not.
It's a continuous, messy, infinite spectrum. Like if you're building an AI for a self-driving car, the steering angle isn't just left or right. It's a continuous floating point number. Audio frequencies, temperatures, light waves. These things have infinite decimal places. They exist on a continuum.
And that transition from the discrete to the continuous leads us right into a profound mathematical minefield.
Oh.
Because if you try to take the rules we just established and blindly apply them to a continuous space, like the real number line, the entire framework shatters.
Okay, this is where things get wild. Why does it shatter?
Because of infinity. If you try to generate a power set meaning every possible subset of the continuous real number line, you end up creating subsets that are mathematically unmeasurable.
Unmeasurable subsets.
Yes, they are sets so infinitely jagged, so paradoxical in their construction, that they literally break the fundamental laws of probability and volume.
Hold on. How can a set of numbers break the law of volume? That sounds like weird science fiction.
It really does. But it leads to geometric impossibilities, the most famous of which is the Banach-Tarski paradox.
Okay, explain that one.
Using the axiom of choice in set theory, mathematicians have proven that you can take a solid three-dimensional sphere, say a solid gold ball, and decompose it into a finite number of disjoint subsets.
Right.
Let's say you cut it into 5 specific pieces.
Okay, I've got a gold ball. I cut it into 5 pieces. Tracking so far.
Then, simply by rotating and translating those 5 pieces in space, without stretching them, without adding any new material, just moving them around, you can reassemble them into 2 solid gold balls, each identical in volume and density to the original one.
Wait. You take one solid object, cut it into 5 weirdly shaped pieces, put them back together like a puzzle, and suddenly you have 2 objects of the exact same size.
Yes.
That completely violates the conservation of mass. That violates the basic fabric of physical reality.
It violates reality because those 5 weirdly shaped pieces are exactly what we call non-measurable sets. They are constructed using an uncountable number of points chosen in such a bizarre, scattered way that they do not possess a well-defined mathematical volume. They exist in the math, but they cannot possibly exist in the physical world.
Okay, that is breaking my brain a little bit.
Yeah.
But how does this relate back to our Python code and our AI?
Yeah.
The AI isn't cutting up gold spheres in its spare time.
No, but it relates to the AI's internal logic board. Remember our probability measure?
Yeah, mapping events to a number between 0 and 1.
Exactly. Well, volume and probability operate on the exact same mathematical axioms. If an AI tries to process a continuous sensor input and its internal sigma algebra accidentally allows for a non-measurable set, the AI will try to assign a probability to it.
Right.
And because the set behaves like the Banach-Tarski sphere, the AI's math will tell it that the probability of event A occurring is 1, and the probability of event A occurring again from the exact same data is also 1, resulting in a total probability of 2.
Which is impossible. Probabilities cannot exceed 1.
Exactly. So the AI's logic board is destroyed. The weight updates in its neural network will literally diverge to infinity or return not a number errors. The AI essentially goes mathematically insane because it tried to measure the unmeasurable.
Wow. Okay, so if the continuous real world is filled with these mathematical landmines, how does our Python program process physical realities like audio files or image sensors without stepping on a non-measurable set and blowing up its own logic?
To prevent paradoxes like Banach-Tarski, we must intentionally restrict the AI's universe.
Okay.
We have to tell the AI you are not allowed to measure every possible combination of continuous points. You are only allowed to measure sensible sets. And the mathematical framework for defining what is sensible on a continuous space is called the Borel sigma algebra.
The Borel sigma algebra. Sigma scholars, listen up, because this is the core of the next phase of your project. How do we define it?
So on a metric space, which is just any mathematical space where you can define a distance between 2 points, like the real number line or a 3D coordinate system, the Borel sigma algebra is defined as the smallest possible sigma algebra that contains all open sets.
Let's translate open sets for the Python developers.
Yeah.
On a 1D number line, an open set is something like the interval between 0 and 1,
Yeah.
but strictly not including the exact endpoints 0 and 1, right? It's the space between them.
Yes, precisely. And in higher dimensions, like a 3D space, an open set is often visualized as an open ball.
An open ball.
Right. Imagine a sphere floating in space, but the incredibly thin, infinitely precise outer surface of the sphere is not included. Only the solid interior points are part of the set.
And why do these open balls save us from mathematical insanity?
Because of theorems 2.3 and 2.4 in the source material you provided for this dive, those theorems state that any open set in a separable metric space can be constructed as the countable union of these open balls.
Ah.
Because they're constructed through countable, predictable operations, they generate a safe, paradox-free Borel sigma algebra. By restricting our AI to only operate within the Borel sigma algebra, we are mathematically guaranteed that every single set our AI interacts with has a well-defined volume. It has a well-defined probability. We just sidestep the Bonatarski paradox entirely.
Okay, that is incredibly elegant.
Yeah.
So the Borel sigma algebra acts as this invisible safety net. It allows our Python program to safely ingest continuous physical data. But as soon as we start dealing with real-world data, we hit another massive, famous roadblock in AI.
Yes.
The curse of dimensionality.
Curse of dimensionality. Let's get into it.
It is an absolute nightmare for data scientists.
Right.
When we deal with real-world data, we are almost never dealing with a single dimension, like a single point on a number line.
No.
Take a standard color photograph. Even a very small image might have 1,000,000 pixels. And each of those pixels has a value for red, green, and blue. To a machine learning algorithm, that image is not a flat square. It is a single data point existing in a space with 3 million dimensions. 3 million dimensions. Humans struggle to visualize 4 dimensions.
Right. And the problem with the space that large is that the mathematical concept of distance breaks down completely. The curse of dimensionality states that as the number of dimensions grows exponentially, the distance between any two randomly chosen points in that space becomes roughly the exact same.
Wait, really?
Yes, in a high-dimensional space, all the data points migrate to the outer edges of the hypersphere. Every point becomes almost perfectly equidistant from every other point.
I want to make sure the scholars understand why this is absolutely fatal for their Python project.
Yeah.
Let's say you're coding a classic classification algorithm like k-nearest neighbors, or KNN.
Sure.
The way KNN works is it looks at a new data point, let's say an image of a dog, and it measures the distance to all the other images in its training set. Whichever images are mathematically closest are the nearest neighbors, and it uses those to guess the label. But you're saying that in a 3 million dimensional space, an image of a dog is the exact same distance away from an image of a cat as it is from an image of an airplane.
Mathematically, yes. The variance of the distance metrics shrinks to basically zero. If every point is the same distance apart, the algorithm cannot distinguish nearest neighbors from furthest neighbors. The AI is essentially blind. It cannot learn the geometry of the data.
So if high-dimensional geometry is fundamentally broken, how do we fix it? We can't just tell a camera to only output 1 pixel.
This is where the Borel sigma algebra provides us with what might be the most counterintuitive, mind-bending mathematical loophole in all of statistics.
Oh, I love a mathematical loophole.
It is called the isomorphism theorem for measures.
Sigma scholars, lean in. This is the blueprint for your class Borel reducer. What is this loophole?
The isomorphism theorem states that any two standard Borel spaces that have the same cardinality, meaning they contain the same class of infinity, like the continuum, are Borel isomorphic.
Okay, give us the plain actionable English translation of that.
In plain English, this means that a data space with incredibly high dimensions, like our 3 million dimensional image space, can be mathematically mapped to a simple one-dimensional line segment, specifically the interval from 0 to 1.
You're saying we can take a 3 million dimensional data set and mathematically crush it down to a single 1D line.
Yes. And it can do this via a bijection, which is a perfect one-to-one mapping that perfectly preserves the entire measurable structure of the original high-dimensional space. The Borel structure is completely unharmed.
That sounds literally impossible. Like, if I smash a 3D glass vase into a 2D puddle on the floor, I have lost the structure of the vase. How can you compress dimensions without losing information?
Because we are not preserving the geometry, we are preserving the measurability. This process is known as Borel isomorphic dimensionality reduction. Because the Borel isomorphism preserves the logical structure of the events, consistent machine learning algorithms, like our k-nearest neighbors, retain their property of universal consistency. So if you map the 3 million dimensional data down to 1D and run KNN on that 1D line, the algorithm will mathematically converge to the correct answer, because it is now operating in a 1D space where the curse of dimensionality simply does not exist. The distance metric means something again.
The source material actually gives a crazy, highly specific empirical example of this working in practice.
It does.
A researcher took a 256-dimensional phone dataset. It's a complex voice recognition audio data. They applied a Borel isomorphic reduction, utilizing orthogonal matrices to pre-process the data before the isomorphism, and crushed those 256 dimensions down to just 16 dimensions.
And the result was incredible.
Yeah. There was only a minimal, almost negligible drop in classification accuracy. The AI could still perfectly recognize the spoken sounds, but with a fraction of the computational load and without suffering from the curse of dimensionality.
It is a profound realization. If we connect this to the broader philosophy of your project, it proves that the informational complexity of a dataset is not strictly tied to its physical geometric dimensions. The audio data might look like it physically needs 256 dimensions to exist in our reality, but its true measurable essence, the actual information required to make a decision, can be perfectly encoded in much less.
So how do our listeners actually code this Borel reducer? Because the theory is great, but Python needs syntax. The source material outlines an exact geometric algorithm for constructing this one-to-one mapping.
The algorithm is elegantly simple in theory. Suppose you have a data point in a two-dimensional continuous space. You have an x-coordinate and a y-coordinate, and both are represented as infinite decimals between 0 and 1.
Go ahead.
Let's say x is 0.A1, A2, A3, and so on, and y is 0.B1, B2, B3, and so on, where the letters just represent the digits.
Okay, so x is something like 0.123 and y is 0.456.
Exactly. Now, to map these two dimensions into a single one-dimensional coordinate while perfectly preserving the Borel structure, the algorithm simply interleaves the digits of the two decimals.
And relieves them.
Yes. You take the first digit of x, then the first digit of y, then the second digit of x, then the second digit of y. So your new 1D coordinate becomes 0.A1, B1, A2, B2, A3, B3, and so on.
Using my numbers, if x is 0.123 and y is 0.456, the new 1D value is 0.142536.
Perfect.
It's a completely deterministic mapping,
Yeah.
and it's entirely reversible. You can easily uninterleave the digits to get your original 2D coordinates back.
Exactly.
So in Python, you would write a function that takes a high-dimensional array, converts the floating point numbers into string representations so you can manipulate the decimals, interleaves those strings character by character in a loop, and then parses the final string back into a single high-precision float.
And by applying this Borel reducer, your Python program takes a continuous, multidimensional physical input, like an image matrix, and flattens it into a mathematically rigorous 1D representation.
Wait, I'm looking at this algorithm and I have to challenge this.
Go for it.
Because this is where the theory hits a massive wall in a real-world coding environment. First of all, let's talk about the geometry. Let's look at the decimal interleaving. If I take 2 points on a 2D graph that are right next to each other physically, say point A is exactly 0.500, 0.500, and point B is 0.501, 0.500, they are incredibly close.
Yes, their Euclidean distance is very small.
But if I interleave their digits, point A becomes 0.50000, point B becomes 0.50000. Wait, okay, those are still close. Let me find a better edge case. What if point A is 0.099, 0.099, and point B is 0.100?
Ah.
Physically, in 2D space, they're right next to each other. But if you interleave them, the 1D values could swing wildly apart on the number line depending on those trailing nines. You are completely destroying the physical metric distance between the points. The space gets shattered.
You have correctly identified the absolute most counterintuitive aspect of the isomorphism. The metric distance of the Euclidean geometry is utterly destroyed. The mapping function is nowhere continuous. It literally violently tears the space apart and rearranges it. But, and this is the magic of measure theory, the informational Borel structure is strictly preserved.
But how can KNN work if the points are suddenly far apart on the 1D line?
Because the KNN classifier, when it's operating under a Borel isomorphism, isn't looking for physical closeness in the traditional human visual sense anymore. It is looking for informational proximity within the new topology.
Okay.
While some points that were close are torn apart, the mathematical proofs guarantee that as the number of data samples approaches infinity, the probability of finding the true nearest neighbors in the interleaved space converges perfectly to the Bayes error limit.
That is wild.
The space looks like a shattered mirror to our human eyes, but to the pure logic of the sigma algebra, the relational rules of the events remain perfectly intact.
That is genuinely mind-blowing. The AI is learning a completely alien geometry. But let me bring up the second, more practical coding challenge for our Edward Littlehigh developers. Python has a standard for floating point numbers called IEE 754.
Oh, yes, the precision limits.
Yeah, a standard float in Python only gives you about 53 bits of precision, which translates to roughly 15 to 17 decimal places. If you have an image with 3 million dimensions, and you try to interleave 3 million decimal digits into a single Python float, you will instantly hit a floating point overflow. Python will just round it off, and you lose all your data. The isomorphism fails.
That is a brilliant point, and it is exactly the kind of engineering hurdle theoreticians often overlook. You cannot use native Python floats for a high-dimensional Borel reduction.
So what do they use?
The scholars will need to utilize Python's decimal module, which allows for arbitrary precision arithmetic, and manually set the context precision to accommodate the total number of intertwined digits. Or, alternatively, they can bypass floats entirely and maintain the 1D mapped values as specialized string arrays or bit arrays.
Right.
But the computational overhead for arbitrary precision is very high, which is why the source material used orthogonal matrices to first reduce the 256 dimensions down to 16 before applying the decimal interleaving. It is a hybrid approach.
So you use a standard linear algebra reduction first to get the dimensionality manageable, and then use the Borel isomorphism to finish the job and guarantee the math. That is a fantastic architectural solution. Okay, so at this point in the project, we have successfully defined our universe of information, we have safely captured the continuous physical world, and we've mathematically flattened it to escape the curse of dimensionality.
We have built an incredibly sophisticated data ingestion engine.
Right. But ingesting and capturing data is not the same thing as intelligence. A hard drive can capture and store data perfectly. A hard drive is not intelligent. Intelligence is about understanding the data you have captured.
And in the paradigm we are building today, understanding is synonymous with predicting. And predicting is synonymous with compressing.
Which brings us to the theoretical heart of this entire project, the universal artificial intelligence paradigm, pioneered by Marcus Hutter and the famous AIXI model.
Marcus Hutter's theory is foundational. It formalizes a concept that computer scientists have suspected for decades. If you want to measure how well an AI understands a data set, you don't ask it multiple choice questions. You ask it to compress the data set.
Let me use an analogy here. If I want to learn calculus, and I decide to just memorize the entire calculus textbook, word for word, like photographic memory style,
Okay.
my brain is storing a massive, massive file of data. But I haven't necessarily learned calculus. I've just recorded the text. If you ask me a novel question that wasn't in the book, I will fail.
Right, because there's no understanding.
Exactly. But if I read the textbook and I actually learn the underlying formulas, derivatives, integrals, the chain rule, I can throw the 500-page textbook away. I have compressed 500 pages of data into a tiny mental program consisting of a few rules. Because I have compressed the data, I actually understand the math. Compression is the realization of the underlying pattern.
That analogy perfectly illustrates the concept of Kolmogorov complexity, denoted mathematically as K of X. In algorithmic information theory, the Kolmogorov complexity of a string of data, X, is defined as the absolute limit on the fewest number of bits required to express that string via the shortest possible computer program running on a universal Turing machine.
So if the data is highly regular, like the digits of a simple repeating fraction or the laws of physics governing a pendulum, the shortest program needed to generate that data is very small. The Kolmogorov complexity is low.
Yes. Conversely, if the data is purely random noise, like the TV static we discussed at the very beginning of the show, there is no underlying pattern to discover. You cannot write a clever, short program to generate pure, unpredictable chaos. The only way to output the static is to write a program that essentially says, print static data, which means the program itself must contain the entire raw data set. The program is exactly as long as the data. It is entirely incompressible.
And this concept is not just some ivory tower theory. It is the basis for one of the most fascinating challenges in computer science right now, the Hutter Prize.
Ah, yes.
Marcus Hutter established a standing cash prize for anyone who can compress a specific 1 gigabyte file of Wikipedia text, known as the NWIC9 dataset, better than the current world record. And the prize isn't just about finding better ways to make zip files.
Not at all.
Hutter's explicit thesis is that because Wikipedia contains a vast swath of human logic, history, physics, and linguistic structure, the only way to compress it to its absolute theoretical limit is to build an algorithm that genuinely understands the physical and semantic world described in that text.
The Hutter Prize acts as a direct objective benchmark for artificial general intelligence. If you can perfectly compress the sum of human knowledge, you have mathematically achieved human-level understanding of that knowledge.
This raises a massive question about the current state of AI. How do modern large language models like ChatGPT or Claude fit into this compression paradigm? Are they actually intelligent, or are they just massive statistical parrots guessing the next word?
Well, under the universal artificial intelligence paradigm, models like DeepMind's Chinchilla 70B are not parrots. They are essentially massive, highly optimized, lossless data compressors.
Really?
Yes, the act of predicting the next word with high accuracy is mathematically identical to compressing the text.
And the sources for today's dive back this up with incredible empirical evidence. Researchers took Chinchilla 70B, a model trained exclusively on text, by the way, and they tested its ability to compress image and audio data.
And the results are just staggering.
Yeah, the language model outperforms specialized, purpose-built compression algorithms like PNG for images and FLAC for audio.
That is a crucial data point. It compressed images to 43.4% of their original raw size and audio to 16.4%.
An algorithm built solely to read text figured out the hidden structural regularities of visual geometry and acoustic physics, better than algorithms explicitly coded by human engineers to do just that.
Exactly.
That proves that the LLM is learning deep, underlying universal structures, not just memorizing words. It's finding the low Kolmogorov complexity programs that run our universe.
And the theoretical mechanism behind this phenomenon is called the minimum description length, or MDL principle. The formula is beautifully simple.
Right.
L of D equals L of H plus L of D given H.
Okay, let's break that equation down for the scholars so they can implement it. L of D is the total compressed size of your data set. That is the final file size you are aiming for, right?
Correct. And that total size is made up of two parts. The first part is L of H. This is the size of your hypotheses.
Okay.
In modern terms, this is the size of your AI model's architecture, the parameters, the neural network weights, the mathematical formulas it has learned. It represents the AI's understanding of the rules.
But the AI's understanding is never perfect. It will make bad predictions. So the second part of the equation is L of D given H. This is the size of the error file. It represents the exact data you need to correct the AI's mistakes, so that you can perfectly, losslessly reconstruct the original raw data.
The MDL principle is entirely a balancing act. If you build a massive, bloated AI model with trillions of parameters that just memorizes the training data, your L of H is absolutely huge.
Yeah.
Even if it makes 0 errors and L of D given H is 0, your total file size hasn't compressed anything. You haven't found a hidden pattern. You just built a giant lookup table.
Right. And on the flip side, if you build a tiny, simplistic model, like a basic linear regression, your L of H is very small.
Yeah.
But its predictions will be terrible. So your error file, the L of D given H, will be massive. And again, you haven't compressed the data.
Exactly. The magic of intelligence is finding the exact optimal balance, where the AI's internal model is just complex enough to capture the deep patterns, minimizing the errors so that the sum of the model size and the error size is significantly smaller than the original raw data.
For your Python project, Sigma Scholars, you're going to code this exact mechanism. You're building a lossless compressor class. Now, a lot of basic tutorials online will tell you to use Huffman coding for this.
I will, yes.
Huffman coding works by assigning a short binary code to common symbols, like giving the letter E a 2-bit code and the letter Z a 10-bit code. But the source material for this project highly discourages Huffman coding
Strongly discourages it.
because it codes on a strict per-symbol basis. It completely ignores the deeper contextual sequence structure. You need to implement arithmetic coding.
Arithmetic coding is fundamentally superior for this task. Instead of assigning a discrete chunk of binary to each individual letter, arithmetic coding encodes an entire sequence of data, like an entire paragraph or an entire image, as a single, incredibly precise fractional number between 0 and 1.
That concept can be really tough to visualize. How does a single fraction represent an entire sequence?
Let's walk through the exact mechanics. Imagine the continuous interval from exactly 0 up to, but not including 1. Let's say your AI is trying to compress the sequence of letters A, I, X, I.
Okay, AIXI.
Right. Your AI model looks at the data and predicts that the letter A has a 45% chance of being the first symbol. Arithmetic coding takes that prediction and restricts our mathematical interval to the range from 0 to 0.45.
Okay, so the interval shrinks. Now we move to the next letter, I.
The AI model now looks at the context. Given that the first letter was A, what is the probability that the next letter is I? Let's say the AI predicts a 60% probability.
Got it.
The arithmetic coder takes 60% of our new, smaller interval, the space between 0 and 0.45, and shrinks the boundaries again to represent that specific sequence.
So you iteratively shrink the interval based on the predictive probability generated by your AI model. The better your AI model is at predicting the next symbol, the larger the probability it assigns to it, and crucially, the less it has to shrink the interval.
Exactly. And a larger final interval is the primary goal, because a mathematically wider interval requires fewer binary decimal bits to uniquely specify a number inside it.
Right.
The source text gives the completion of this example. Because the AI model successfully predicted the sequence AIXI with very high confidence, the final interval was wide enough that the program only needed 7 bits to encode the entire sequence.
Yeah.
0101010.
But let me flag a massive Python implementation issue here for the developers. As you iterate through a large sequence, say an audio file with thousands of data points, shrinking this interval over and over again, the interval boundaries are going to become infinitesimally close together.
Very quickly.
Yeah, very quickly the difference between the upper and lower bounds will fall below Python's 64-bit floating point precision limit. The upper and lower bounds will just round to the exact same number, the interval will collapse to 0, and your arithmetic coder will fail. How do they code around that?
This is a classic challenge in arithmetic coding known as underflow. The standard engineering solution, which the scholars must implement in their lossless compressor class, is continuous rescaling.
Continuous rescaling. How does that work?
As soon as the upper and lower bounds of the interval share the same leading binary digit, you know that digit is locked in. It will never change no matter how much more you shrink the interval.
Oh.
So you stream that locked bit out to your final compress file, and you dynamically rescale the remaining interval back up to a wider range. This allows you to use standard integer arithmetic in Python to simulate infinite precision intervals.
That is a pro tip right there. Stream the locked bits and rescale. So your Python program will take the 1D Borel reduced array from the previous phase, and it will attempt to compress it using this predictive arithmetic coding loop.
And the test of intelligence for your code here is brutal but entirely objective.
You calculate the size of your compressed data file plus the size of your Python decoder script and model weights. If that combined size is smaller than the size of the original raw data array, congratulations. Your Python program has discovered a hidden pattern in the universe. It has mathematically demonstrated intelligence.
It really is a remarkable milestone, but, and this is a profound caveat, there is a fatal theoretical flaw in lossless compression when it comes to true, real-world artificial general intelligence.
Right, because lossless compression, by definition, mandates that you must retain every single bit of the original data. You must be able to perfectly, flawlessly reconstruct the original file from the compressed state.
And as we established at the very beginning of the show, the real physical world is incredibly noisy.
This goes right back to the TV static. If I feed my AI a data set containing the static on a TV screen, the minimum description length principle says the shortest program to encode that static is just to memorize the static. A lossless compressor is mathematically obligated to perfectly reconstruct the chaos.
Yep.
It will spend vast, paralyzing amounts of computational and cognitive resources memorizing meaningless, high-entropy noise.
Which is cognitively fatal. If a human being tried to memorize the exact geometric coordinate of every single blade of grass in a field in order to understand the conceptual abstraction of a field, they would be biologically incapable of functioning.
We just freeze up.
Exactly. To survive in a noisy universe, an intelligence must learn to forget.
Which brings us to the climax of the project, the art of abstraction, lossy compression, and subsigma algebras.
Lossy compression is the process of intentionally removing unnecessary or less important information from a dataset. It relies on the concept of perceptual or statistical irrelevance, and we interact with this technology every single day. The most ubiquitous examples are MP3 audio files and JPEG images.
Let's look at the mechanics of an MP3. When you compress a master recording of a song into an MP3, the algorithm doesn't just try to find repeating patterns. It uses a physiological model called psychoacoustics. The algorithm mathematically calculates which high-frequency sounds are physically masked from the human ear by louder, lower-frequency sounds occurring at the exact same time. The MP3 encoder realizes you literally cannot hear the high frequencies, so it just deletes them.
That throws the data in the trash.
Yes. When you decode the MP3, that data is gone forever. But you don't notice, because the algorithm understood the biological limits of human perception.
Similarly, when an algorithm creates a JPEG image, it doesn't store the exact hexadecimal color code for every single pixel in a blue sky. It looks at a block of pixels, calculates that they're all statistically close enough to the same shade of blue, and it averages them out to a single value.
It deliberately forgets the microscopic variations in the sky to save massive amounts of space.
Yes.
So in the context of our mathematical Python framework, how do we formalize this intentional forgetting?
The formal theory of this abstraction is governed by a concept known as the information bottleneck, or the ID principle. The mathematical formula for the IB Lagrangian is a minimization problem. Minimize the mutual information between x and z minus beta times the mutual information between z and y given x.
Okay, let's translate that Lagrangian equation into plain English for the developers. What are these variables? X, Z, Y.
Let's break it down. X is your raw original input data. Z is the new, deeply compressed, lossy representation of that data that the AI is trying to create. And Y is your specific target, the actual outcome you want the AI to predict or understand.
Okay, tracking. And what is the I?
I stands for mutual information, which is just a measure of how much knowing one variable reduces your uncertainty about another.
So the first part of the equation, minimizing the mutual information between X and Z, that is the bottleneck. You are actively trying to minimize the mutual information between the original data and the compressed data. You want the compressed representation Z to be as small and as forgetful as possible. You want to crush it.
Yes, that forces the lossy compression. But if you just minimize it to 0, you would just delete the entire file. You would forget everything.
Which doesn't help anyone.
Right. So the equation has a counterweight. Minus beta times the mutual information between z and y given x. This second term forces the AI to ensure that the tiny compressed representation z still retains maximum predictive information about your specific target outcome, y.
So what does this all mean in practice? Let's use a physical analogy. Think about packing a suitcase for a trip.
I like this.
Lossless compression is like buying a giant vacuum seal bag and trying to shrink down every single item you own in your house so you can carry your entire house with you. It's exhaustive and exhausting.
Absolutely.
Lossy compression, driven by the information bottleneck, is totally different. First, you check the weather at your specific destination. That destination is your target, Y. You realize it's going to be snowing. So you pack a heavy coat, boots, and gloves. You intentionally throw out the shorts, the swimsuits, and the sandals. You don't bring them. You pack only exactly what you need to survive the expected outcome. But to do that, to know what to leave behind, requires a deep understanding of the destination.
That is a phenomenal analogy. And this is exactly where we mathematically fulfill the second ultimate paradigm of your mission today. Lossy compression is intelligence where sufficient information is retained to perform the expected outcomes. True. Abstract understanding requires knowing exactly what data to throw away.
And how does this connect back to the mathematical foundation we built an hour ago? How does lossy compression relate to the sigma algebras from the beginning of the show?
It connects beautifully, completing the entire theoretical circle. Mathematically, lossy compression is the intentional, calculated selection of a sub-sigma algebra.
Is sub-sigma algebra? Explain the connection.
Remember, our original, fully validated sigma algebra contained every possible measurable event in our AI's universe. It was the complete exhaustive syllabus.
Right.
While a sub-sigma algebra is a smaller, restricted collection of events that still obeys the 3 mathematical axioms, but it operates at a much lower resolution. By intentionally choosing a sub-sigma algebra, the AI is deliberately restricting its own information state to a coarser granularity.
It is actively choosing to be less informed.
Yes. It is deliberately clumping functionally identical states together and mathematically refusing to distinguish between them. If the AI sees a blue pixel and a slightly lighter blue pixel, the full sigma algebra measures them as 2 distinct events.
But the sub-sigma algebra clumps them together as a single event called blue.
Exactly. The AI is mathematically blinding itself to the microscopic noise so it can focus entirely on the macroscopic signal.
The source material actually discusses a cutting-edge example of this happening in modern LLM architecture, specifically looking at a mechanism called the Conditional Information Bottleneck, or CIB, embedded within transformer models.
Yes, the CIB.
Researchers analyzing how transformers process language found that the CIB acts as a literal, high-pass semantic filter.
How so?
As the AI processes a long sequence of text, the bottleneck mathematically penalizes low-utility, highly predictable filler words like the and a. It effectively excises those words from its deep internal representations. It just drops them.
Fascinating.
But it strictly preserves the high-entropy peaks, the complex, unexpected words that carry the actual logical reasoning traces and semantic meaning of the sentence. It doesn't just randomly truncate the data to save space. It maximizes the average information rate by distilling the computation down to its essential abstract content.
And for the Sigma scholars, this brings us to the final class you must construct for your Python architecture class, sub-sigma algebra. You are going to write a custom loss function that explicitly represents this information bottleneck trade-off. Your program will take the data from your Borel reduced array, and it will intentionally delete data points.
I really want to emphasize how radical this is for a standard coding project. You are going to write code whose specific ultimate purpose is to throw away perfectly good data.
You must apply lossy compression. Your algorithm will evaluate the mutual information, and it will delete points that have low predictive value for your target label.
Okay, give us an example.
For instance, if your ultimate target Y is predicting foams to understand human speech, your code will actively delete the acoustic frequencies that are statistically irrelevant to differentiating a P sound from a B sound. The background hum of an air conditioner? Deleted. The specific pitch of the speaker's voice? Deleted.
And the beta parameter in that information bottleneck equation acts as your tuning dial. If you set beta very low, the bottleneck dominates and your AI throws way too much data, becoming stupid.
Right.
If you set beta very high, the target prediction dominates and your AI acts like a lossless compressor, memorizing the noise again. You have to write a training loop that finds the perfect beta balance.
And that leads to the ultimate test, the final grade for your entire Python architecture. Your program must ingest a data set. It must throw away a massive portion of the original data, let's say 80%.
Wow, 80%.
It must obliterate the noise and operate solely on a drastically reduced subsigma algebra containing only 20% of the original information. But using only that remaining 20%, it must still maintain a 95% accuracy rate on predicting the expected target outcome.
If your code can do that, if it can throw away 80% of reality and still perfectly predict the future, you haven't just built the statistical calculator. You have proven that your Python agent has achieved true, human-like abstract intelligence. It knows what matters, and it intrinsically knows what doesn't.
There is a profound philosophical irony embedded in all of this, which actually sits at the center of a major debate among AI theoreticians right now.
Oh.
Marcus Hutter, the creator of the AI-XI model, argues that true, pure artificial general intelligence must rely exclusively on lossless compression.
Wait, why? If we just spent the last 20 minutes proving lossy compression is better for handling noise, why does the godfather of the theory demand lossless?
Because Hutter views intelligence from a universal, almost godlike perspective. His argument is that if an AI discards information as noise because it doesn't seem relevant right now, it might accidentally throw away the key to a deeper, undiscovered pattern in the universe.
Oh, I see.
What looks like meaningless static today might be recognized as the cosmic microwave background radiation tomorrow. A perfect, omniscient intelligence like AI-XI never wants to forget anything because it operates on infinite compute and infinite time.
But that is not how biological intelligence works. Human cognition, the very standard of intelligence we are actually trying to replicate in these machines, is fundamentally biologically lossy.
It is.
We have to sleep for 8 hours a day just to physically prune our neural connections and flush data out of our brains.
Yeah.
We forget almost everything that happens to us every single day. I don't remember what I had for breakfast a week ago because that data doesn't help me survive.
No, it's irrelevant.
We only remember the expected outcomes, the vital lessons, the trauma, the joy. The details just blur. Human intelligence is a masterclass in lossy compression.
It is a fascinating mediation between the mathematical ideal and the physical reality. Lossless compression is the benchmark for an omniscient, uncomputable intelligence with infinite resources. Lossy compression, the information bottleneck, is the benchmark for an embedded, physical intelligence that must survive in a messy, noisy universe with a strictly limited biological or silicon energy budget.
Both are valid definitions of intelligence.
Yes, but they operate at entirely different scales of reality.
We have covered an incredible, almost overwhelming amount of ground today. Let's synthesize the epic computational journey you Sigma scholars have just coded.
Let's do it.
You didn't just write a simple automation script. You built an entire universe of information from the ground up by defining a rigorous Sigma algebra. You ensured your AI mathematically understands the concept of an event, the concept of an empty set, and how to logically deduce complements and unions without crashing his memory.
Then you confronted the infinite, continuous, paradoxical physical world and you tamed it. You utilized a Borel isomorphism to mathematically crush high-dimensional, curse-inducing data down to a manageable, one-dimensional number line.
Perfectly preserving its measurable informational structure or completely rewriting its geometry.
Exactly.
From there, you proved your AI could learn by squeezing that data. You implemented a lossless compressor using predictive arithmetic coding, handling floating point underflows, and dynamically rescaling intervals. You proved the minimum description length principle, that finding the shortest algorithmic program to generate the data is literally identical to discovering its underlying universal patterns.
And finally, you elevated your AI to true human-like abstraction. You implemented the information bottleneck, allowing the AI to perform lossy compression. You taught it how to mathematically select a coarser sub-sigma algebra, deliberately ignoring 80% of the noise in the universe so it could hyper-focus on accurately predicting the 20% of reality that actually dictates its survival.
You built the fundamental mathematical architecture of intelligence from scratch. That is absolutely bussin'.
Before we sign off, I want to leave you and all our listeners with one final, slightly mind-bending thought to explore on your own.
I'm ready.
We have just spent the last hour establishing that human memory and cognition are highly optimized, lossy compressors. We navigate the physical world by creating a drastically reduced sub-sigma algebra of reality. We actively filter out millions of sensory inputs and keep only what is strictly necessary for our evolutionary survival and reproduction.
Right. We check the weather, and we only pack exactly what we need in the evolutionary suitcase.
Exactly. But this raises a terrifying question. If our entire biological perception of reality is just a heavily compressed, lossy projection, what massive foundational features of the actual universe has our evolutionary algorithm simply compressed out and deleted as noise? Are there entire dimensions, fundamental physical forces, or complex realms of information interacting all around us right now that we are completely biologically blind to simply because knowing about them didn't help our ancestors escape a lion on the savannah?
That is.
We might not be experiencing reality at all. We might just be living inside a severely compressed ZIP file of true reality.
A ZIP file where the original data was thrown in the trash millions of years ago and can never, ever be recovered. That is deeply unsettling and utterly amazing. Sigma scholars of Edward Little High, good luck with the Python code. Watch out for those floating point limits and keep questioning the limits of your own Sigma algebra. We will see you next time on The Deep Dive.